Okay, so this presentation will introduce the very basics of valence shell electron pair repulsion theory. You will need your Lewis structures from before to use them for Vsepr. Our objectives: we will define electron domain, bonding domain, lone pair electrons, unpaired electrons, central atom, steric number, electron geometry, and molecular geometry, which is a respectable amount of vocabulary for this particular section. So just be warned, if you have trouble absorbing vocabulary, you're going to want to go over this multiple times. We'll define the basic concepts in valence shell electron pair repulsion theory, which from now on I will call Vsepr, just for my own sanity. We will use Lewis structures with Vsepr to predict molecular shapes, including approximate bond angles and dipole moment. Very, very loosely on that one. We'll get into more of it in another presentation. Vsepr makes 5 basic assumptions. These assumptions almost always work when determining the shape of molecules, which is why we teach the theory. So first, electrons repel other electrons. This assumption is fairly safe and extremely well documented. Second, there are 2 types of electron groups, bonding and non-bonding. We'll get into more of that on the next slide, but in general, as a concept, some electrons on an atom will bond, others will not. Third, electron domains will arrange themselves around a central atom to be as far apart from other electrons as possible in order to minimize the interaction between domains. Now, what am I talking about here? Electron domains are roughly talking about orbitals, where you can fit 2 electrons in an orbital. In an electron domain, you can fit more than 2 electrons. So this is not an exact correlation, but it's the same idea. We're going to have a certain pathway that the electrons can follow, and outside of that pathway, they won't be there. So when we're talking about electron domain, we're talking about not so much an atomic orbital, but a region in space where electrons can be. More of that on the next slide. Fourth assumption, lone pair domains, which are non-bonding with electrons directly on the central atom, are larger than bonding domains. So this assumption is based on the fact that a bonding domain is shared between 2 nuclei, which effectively cancels some of the charge of those electrons in the bond. A lone pair domain has interaction with only 1 nuclei, the one on the central atom, and therefore it has a larger effective nuclear charge, which is more effective at repelling other electrons. Fifth, double bonds occupy more space than single bonds. There are 4 electrons in a double bond, and there are 2 involved in a single bond. As you would expect, 4 electrons will take up more space than 2 electrons, which is where this assumption comes from. So there you have it, the basic ideas, the assumptions that shape this theory. Let's talk a little bit more about the electron domains. Vsepr theory is used to predict the 3-dimensional shape of molecules based on how many electron domains there are. So we need to know how many electron domains we have and what type they are. We have bonding and non-bonding domains. The bonding domains are single bonds, double bonds, triple bonds. Bond is in the word. And the non-bonding domains are lone pairs and unpaired electrons. So we have a nice example of bonding domains over here on carbon dioxide. We've got 2 double bonds from carbon going to each oxygen. And when we look at that, we call that 2 domains. And the number of electron domains on a molecule is known as the steric number. So carbon dioxide has a steric number of 2. 2 electron domains, both bonding, steric number of 2. We can look at this other example here of ammonia, and it conveniently has a nice lone pair. So we've got an example of a non-bonding domain. The lone pair is 2 electrons on the top of nitrogen in our Lewis structure. And then we have 3 singly bonded hydrogens, for a total of 4 electron domains. 3 of them are bonding, 1 of them is a lone pair domain. Now, I mentioned unpaired electrons as another possible domain. If you remember the exception to the octet rule where you have an odd number of valence electrons, yeah, that is the unpaired electron. Unpaired electrons count as their own domain and they're highly reactive. In fact, they're referred to as free radicals. In case you were wondering, that is what a free radical is. It has an unpaired electron. Okay, so ammonia, in summary, steric number of 4. Steric number, in the end, counts the number of directions off of the central atom where there is significant electron density. So this means that an electron domain is not an atomic orbital. Though there is an overlap in the ideas here, there is also a distinct difference. You can have up to 6 electrons shared between atoms, and they are all shared along a single axis, which counts as a single electron domain. But atomic theory tells us this would involve 3 atomic orbitals. So these are 2 distinctly different things. One deals with the direction where the electrons are, and the other deals with the probability function of where those electrons are. We don't need to know exactly where they are. We just need to know the general direction they're in. All right, so let's practice at determining steric number on our own. Calculate the steric number of water. And I will tell you right now, you're going to want to write the Lewis dot structure and then count your electron domains. I'm going to pause for a bit to let you do that. Okay, so we draw the Lewis structure with the lowest terminal charge, and here we have our water. All right, we have lone pair here, a lone pair there. So we've got 2 lone pairs. We have 2 single bond hydrogens. So 2 bonding domains, 2 non-bonding domains gives us a steric number of 4. All right, so how do we determine shape from Vsepr and Lewis structures? Well, we first start with the Lewis structure of the molecule. We then determine the steric number on the central atom, which is something that we just did. And then finally, we will use the steric number to predict the electron pair and molecular geometries using Vsepr geometry table. So what is this table that I speak of? This is the table. Okay, so we have our basic geometries. I'm going to outline those in yellow. These are if everything is a bonding domain and all of the outer atoms are the same. Now, these basic geometries are how you spread out the electrons as much as is possible. If, however, you have some non-bonding domains or you have something that doesn't quite match up, you get into these geometries, or you get into a distortion of the basic geometry. We'll talk more about that later. So in these geometries, you can see you're adding increasing number of lone pairs, and the resulting shape is different. So for example, if you go to a steric number of 4 and you add 1 lone pair domain, the shape that you can make with the bonds and the atoms, because you can't make a shape with electrons, is trigonal pyramidal, or trigonal pyramid. If you take another one, you put another lone pair on there, you end up with what's called a bent shape. We will go over more of this in another set of slides, but for now, we can identify steric number, our bonding domains, our non-bonding domains, and find where we are on this chart. Let's give that a shot. Determine the molecular domain for PBr3, and I'm going to give you that the electron geometry should be tetrahedral, so I can use just that portion of the table. So we need to figure out what the Lewis structure for PBr3 is. Go ahead and follow those guidelines, and then in the next slide, we will have the answer. Okay, so I have my Lewis dot structure for PBr3. We had 26 valence electrons, so we end up with a lone pair on the phosphorus. It has 3 bonding domains and 1 lone pair domain and has a total steric number of 4, as previously stated in the problem. And so when we look for the one with 1 lone pair domain, we end up with trigonal pyramid. So that is the shape that we would expect for PBr3. In summary, valence pair electron repulsion theory, Vsepr, says that electrons repel other electrons. There are two types of electron groups, bonding and non-bonding. The electron domains will arrange themselves around a central atom to be as far apart from the other electrons as possible in order to minimize interaction. Sorry. Lone pair domains are larger than bonding domains, and double bonds occupy more space than single bonds. Finally, electron geometry is what you get from steric number, and that's how many directions the charge is. Molecular geometry is what you get from the actual bonds and atoms. What is the shape that's left over?